So Bohr, using his model, theorized a couple things about energy in the form of EMR. Number one, EMR is emitted when an electron falls down from one level to a lower level. And that's how we end up with this emission spectrum. He also theorized that energy in the form of EMR is absorbed to make an electron jump up from one level to a higher level. And that is where we get this absorption spectrum from. Now we can take this emission spectrum for hydrogen and actually determine what wavelengths of light are present as those energy changes happen. Again, because we have this equation, large changes in energy are going to give us larger frequencies of light being emitted. So if I have an electron up here on the 6th energy level, if it falls down to the 2nd energy level, I'm going to have a relatively high energy change and a higher frequency of light being emitted, like this violet light. Whereas if I have a small energy change between the 3rd and 2nd energy level, I'm going to have a lower frequency of light being emitted. So this is what is called the Balmer series. And we can actually calculate, based off the frequencies of light that are emitted, we can calculate the wavelengths and determine the wavelengths that we should actually observe. Now, we'll jump ahead now and look at this energy level diagram and try to determine if we have electrons falling from higher energy levels to lower energy levels, how many possible energies of EMR, frequencies of EMR, can be emitted based off of this energy level diagram. Now again, electrons can only exist at these stable states, at these energy levels. That's the only place where these electrons are going to exist in a stable state. If I have an electron on the 4th energy level, it can undergo a couple of different energy changes. One between the 4th and 3rd. It can also fall down to the 2nd, or it could fall down to the 1st. So I could have 3 different energies emitted if that electron were to fall in those different ways. An electron on the 3rd energy level could fall down to the 2nd level or to the 1st, and then an electron on the 2nd level could fall down to the 1st. So I have 6 possible energy changes for this energy level diagram. Now, based off of this energy level diagram, let's determine the wavelength of EMR emitted as an electron drops from the 3rd to the 2nd energy level. So let's look at that energy change and try to describe the photon of light that would be emitted there. Now, we have this equation which allows us to determine frequencies if we know the change in energy. And for this energy level diagram, the change in energy is the difference between the 3rd and 2nd energy level. This 3.4 electron volts and 1.5 electron volts. It's a difference of 1.9 electron volts. It's going to be my change in energy. I can calculate the frequency by taking my 1.9 electron volts and dividing by Planck's constant, 4.14 times 10 to the negative 15 electron volts per second. And I get a frequency of 4.59 times 10 to the 14 hertz. If I want, I can use this relationship, the universal wave equation, to convert between frequency and wavelength. C is the speed of light. I can find the wavelength emitted as an electron falls from the 3rd to the 2nd energy level is 650 nanometers. So that corresponds to red to yellow, so maybe orange light being emitted as that electron falls from the 3rd to the 2nd energy level. Now we can skip ahead too. If I have green light, I have the same energy level diagram, but does green light have enough energy for an electron at the 1st energy level to be moved up to the 2nd energy level? Now to calculate if that energy change is enough, we can combine those equations from the previous slide. The universal wave equation and the equation using Planck's constant and frequency to get this relationship. So I can calculate my change of energy this way, where it's 4.14 times 10 to the negative 15 electron volts per second. C is the speed of light. So that's speed of light. So multiplied by the speed of light, 3.00 times 10 to the 8 meters per second, divided by my wavelength, which is 500 nanometers, so 500 times 10 to the negative 9 meters. I do this calculation and I get an energy change of 2.48 electron volts. Now that energy change is not enough. 2.48 volts is not enough to get that electron all the way up to the second energy level. And those electrons can only exist at these stable states, at N1, N2, N3, or N4. So that electron would fall back down. It does not have enough energy, a green photon of light, to actually allow that electron to jump up to the second energy level. So we can use Bohr energy level diagrams and Planck's constant and this relationship between Planck's constant and energy to actually make calculations that allow us to determine the characteristics of light that is emitted or absorbed, or the changes in light that would be absorbed using these different tools.